This is the next example of electrical system in which we will discuss that how we can form the state equation of this circuit. Here the output voltage is V1 and the input is basically the current source. So starting with this example, we must know that in series the current remains same, but in parallel the voltage remains same. So we have several elements here. C1, L1 are in parallel, so this voltage will remain same. That is VC1 is equals to VL1. Similarly, VL3 is equals to VC2 as these two elements are in parallel. So first of all, we have to form this equation or different nodes of voltages and current using KCL and KVL. So at node x1, I will write at node x1 we have a voltage V1 which is equals to the voltage of capacitor, as this capacitor 1 is parallel with the inductor 1. So these two voltages are equal, as capacitor 1 and inductor 1 are in parallel. Second thing is the node equation here, the current equation. This current is entering, this current of capacitor will leave, this current will leave. So I will write this equation using KCL is I2 is basically IL2 is equals to IC1 plus IL1. I will say this is my equation 1, this is my equation number 2. Secondly, at node x2 we have a voltage V2 which is equals to VC2, or the inductor voltage VL3, because L3 is present with parallel with C2. Similarly, if I want to write the current equation at this node x2, this is my complete node x2. Here this current is entering, this I3 will be leaving, this capacitor current will be leaving here, similarly the inductor current too. So I can write a current equation using KCL here. This is my input, I is equals to IL3 plus IL2 plus IC2. This is my equation number 3. This is my equation number 4. But similarly, we can write loop equation. I write loop equation here. In this loop, this capacitor voltage V2 or VC2 or VL3 is here. This loop equation will be equals to VC2 is equals to VL2 plus VC1. So I will write the loop equation. This will become VC2 is equals to VL2 plus VC1. I can write this equation in terms of all inductor voltage. This VC2 is equals to VL3. Similarly, VC1 is equals to VL1. So I can replace it as VL3 from equation 3 is equals to VL2 plus VC1 will be equals to VL1. In terms of current, this equation will become LD L3 D I3. Similarly, VL2 will be L2 D I this is L2 d I2 plus VL1 is L1 d I1. So this whole equation, every term in this equation involves derivative operator. I can remove this derivative operator if I use an integral here, multiplying this whole equation by 1 by d, or you can say integrating this whole equation will reveal. I will say that multiplying the above equation by 1 over d, for basically you are integrating this equation. This will become L3 I3 is equals to L2 I2 plus L1 I1 plus K. This is K is basically constant term which comes due to initial condition. Usually we take this K equals to 0 for our convenience because we consider no initial condition. So this equation will be L3 I3 is equals to L2 I2 plus L1 I1. So I will name this equation as equation 5. Why I made this equation? Basically this equation reveals one important thing. What is that? If we want to decide state variable here, we can see that we have 5 energy storing element, one inductor, second inductor and third inductor, similarly 2 capacitor, 3 inductor and 2 capacitor. Total 5 energy storing element means that we may have 5 state variables. But from this equation we see that this is a linear dependent equation, means one current of one inductor current depends on the other 2 inductor current. So these all 3 inductor current IL1, IL2 and IL3, basically this is I inductor current. I will write it as inductor current IL1, this is IL2, this is IL3, similarly this is IL3, this is IL2, this is IL1, similarly this is IL2, this is IL1, this is IL3. All these inductor current depends on are not independent variables if one of these inductor current depends on the other 2. So we know that state variables are basically linear independent quantities, and these or one current is dependent on the other 2. So we should take only 2 inductor current here and these 2 capacitor voltage. Third one can be evaluated with this linear equation. So we need to evaluate any 2 of these inductor current using a state variable, and the third one can be evaluated with this equation. So no need to evaluate 5 state variable. Instead we can see that these are the linear dependent. One of the inductor current is linear dependent on the other 2 inductor current. So if you evaluate any 2 of these 2 inductor current, then we can evaluate the third one. So here we can take only 4 state variable, that is 2 capacitor voltage, any two inductor current. So my state variable will be state variables will be x1 is basically my capacitor voltage V1 is equals to Vc1. Similarly, x2 is equals to V2 is equals to Vc2. Similarly, x3 is my inductor current IL1, or we can say I1. Similarly, x4 is equals to inductor current 2 is equals to I. Inductor current 2 is basically I2. Okay, and the fifth state variable is my input, which is I, which we take it as U. So we can evaluate these four state variable, and the fifth inductor current can be evaluated with the help of these two state variables. So using equations 1, 2, 3, 4, we can evaluate it easily. What I can see here is that if I want to evaluate Vc1, for Vc1 I can use equation number 2. This equation 2 is contained IC1. Mathematical model of this capacitor is basically IC is equals to CdVc. So from IC1 I will get dVc, that can be used to evaluate x1 dash. X1 dash mean I want to get, or x1 dash basically I want dVc1. So dVc1 can be available from equation 2. Here I will copy this equation here, so I will write using equation number 2, which is equals to I basically IL2 is equals to IC1 plus IL2 is equals to IC1 plus IL1. So IL2 is basically my x4. IC1 can be written C1 dVc1, which is my x1 dash, plus IL1 is basically x3. So I can write this equation x1 dash is equals to x minus 1 over C1 x3 plus 1 over C1 x4. This is my first state equation A. For dVc2 or x2 dash, I will use this equation. This equation involves IC2, from where I can get dVc2. So I will use this equation here, which is equation number 4. Using equation number 4, which is basically I is equals to I3 plus IC2 plus IL2. So here this inductor current IL3 is not my state variable. I selected IL1 and IL2 as my state variable. Anyone can select IL1 and IL3, IL2 and IL3, any two of these inductor current, because the third can be evaluated from the equation number 5. So this equation, this IL3 can be written in terms of IL2 and IL3. From this equation 5 I can write IL3 in terms of IL2 and IL1. So I will replace this input as U. This IL3 will be written in form of in terms of L2 and L1, IC2 is equals to CD VC2 plus IL2 is here. IL1 is my X3, IL2 is my X4, so I can write U is equals to L2 X4 plus L1 X3 L3 plus C, this is C2, this is C2 dVC2, this is basically my X2 dash, and this is IL2 which is basically my X4. So rearranging this equation to evaluate X2 dash, my X2 dash will be equals to minus L1 L3 into C2, this is X3 minus L2 plus L3 over L3 C2, this is X4 plus 1 over C2 U. This is my equation V. So for X3 dash, which is basically V IL1, we know that VC1 is equals to VL1, so I can write VL1 as VC1 is equals to VL1 is L1 DIL1. This is basically can be written as X3 dash is equals to X1 over L1. This is my equation C. Similarly, I can find the fourth state variable X4 dash. We know using equation number using this equation, VC2 is equals to VL2 plus VC1, the KVL loop equation, which was VC2 is equals to VL2 plus VC1. I will name that equation so it will be easy for everyone. That is this equation. I will name this equation my equation 6. So using equation number 6 here, I have written this VC2 is equals to VL2 plus VC1. This is by using equation number. VC2 is my X2 L2, VL2 will be L2 DIL2 plus VC1 is X1. So my X2, sorry, X4, L2 is my X4, X4 dash will be equals to minus 1 over L2 X1 plus 1 over L2 X2. This is my equation D. So all of these four state equations are now evaluated, which are X1 dash, X2 dash, X3 dash and X4 dash. So I can write the state space matrix here. I will not write here, I will just draw the format. I will just draw this format here. This will be my for using x1 dash, x2 dash, x3 dash and x4 dash, we can write the state space representation here. This can be done the similar way as we have done in the previous example, so I'm not repeating this. So here what we learned, that we can evaluate a state equation of this system, but here the speciality is that we have more than we have 5 energy storing element, but in which we have an equation which reveals that the one inductor current depends on the other two inductor currents, so all three inductor current are not linear independent. So these are not all three are not the state variables. So we selected the 4 static variables here, and we use these equations here to find x1 dash, x2 dash and x3 and x4 dash, and this can be written in form of state space representation. So this is the last example of this electrical system. I hope that this will be clear to you. Kindly do practice it. This will be more clear if you start practicing it on your own, and if you have any question you can ask in the live session. Please try to practice this question at your own as well. Here one important thing which you should think, that this is really difficult, that we have to find that these current L2 IC1 and where is that equation? Yes, using equation 5 we revealed that these 3 inductor current are not linearly independent. One inductor current depends on the other 2 inductor current. So there is a discussion which you should know. The dependency of I3 on I1 and I2 as shown in this example may not be readily observed, or we can see that it cannot be easily observed. In that case, the matrix state equation for this example would be written in 5 state variable. If anyone could not readily see this linear independency or dependency, then he may reveal the 5 state variable. So that 5/5 equation will be of no use, but we will get all 4 important state variables. These examples in the section are fairly straightforward. In general, it is necessary to write more than just the number of state equations because other system variables appear in them. So it is not usually easy to see the linear dependency. It is straightforward example and we have revealed it easily, but if anyone didn't reveal that thing, he may take 5 state variable and have 5 state equation. But for the concept of linear dependency and linear independency, if one take only 4 variables, these state equations are enough to represent this system. Okay, finally In this week, we will perform modeling of a DC servo motor. And DC servo motor, what do we mean by the servo motor? A servo motor is basically a rotary actuator or a linear actuator that allows for precise control of angular or linear position, velocity, and acceleration. Basically, servo motor is used to perform precise control of these three parameters: position, velocity, and acceleration. So here we will perform modeling of the system. This system contain electrical system as well as mechanical rotational system. So combining these two systems, we have a DC servo motor here. This is the basic model of a DC servo motor. Here, this is basically the armature circuit. This is my field circuit, and this is basically the shaft of the motor. Actually, the development of a torque here at the output of the motor depends on the two quantities. One is basically the armature current IM, and second is basically the field current IF. So you can say armature current as IA as well. So for any given motor, if we want to control this output, that is torque, this torque can be adjusted with the help of these two parameters, that is armature current, second is the field current or the flux due to this field current. So these are the two parameters, adjustable quantities. One are flux, this flux is basically due to the field winding, second is the armature current. So we can write this output torque can be adjusted with the help of two parameters. One is flux, that is due to the field current, second is the armature current IA, or you can write IM. This is basically the proportional constant. This term is directly proportional to the flux, and this IM, this is equals to, and we use proportional constant here. Secondly, there are two modes of operation. This is the same control. These are the two same methods. One is basically the armature control mode, in which we have field current is held constant or field is fixed while we are controlling or adjusting the voltage at the armature, so we can control the armature current. Similarly, the second method is to control the field, and the armature current is held constant when we apply adjustable voltage to the field. Here we will perform fixed field method or armature control method. Here we will control the armature voltage and we will control the armature current, and there will be a fixed DC source at field winding. So a constant field is obtained by separately exciting the field from a fixed DC source. We applied a fixed DC source at the field winding, so the flux is produced by the field current is therefore essentially constant. As we have applied a fixed source, the flux will be constant or fixed. So I can write this equation number 1, K3 phi Im. This phi is now also constant because my field current is constant, because my field is connected to a fixed source, so field current is constant, so this flux will be constant. This K3 phi, these two terms are constant. K3 is already a constant, phi is now constant because we have a fixed DC source at field. So we replace this K3 phi with KT, and my equation number 1 become KT Im. That means in this method we can control this torque only by adjusting the armature current. So when the motor armature is rotating, a voltage EM is induced in the that is proportional to the product of flux and speed. Because the polarity of this induced voltage or opposes the applied voltage, it is commonly called back EMF. When motor starts rotating, here a back EMF is generated, which is of opposite polarity or relative to this input. So we called it back EMF, which is induced EMF. This is EM, which is directly proportional to the flux and the speed. Since here we have a constant flux because of constant field, so we can write EM is equal to K1 phi Wm. This induced or back EMF depends on flux as well as on the speed, as we discussed it here. So but we know that flux is also constant, so these constant can be replaced with a new constant. K1 phi is replaced by Kb omega m, and this omega means angular velocity can be replaced with the change in displacement means d theta m. I can write this velocity in terms of displacement. So this is basically the induced EMF and this is the parameter. So this is overall circuit diagram of our circuit of our system, DC servo motor. We have armature circuitry, field circuitry, and finally a mechanical rotational system. So if I want to write the equation of this loop, the armature inductance and the resistance are labeled as Lm and Rm. The KVL loop equation will be equals to EA is equals to VR plus VL plus this back EMF EM. And similarly, the inductor voltage, similarly the capacitor resistor voltage will be replaced by R into R and LD I, the mathematical model of resistor and this inductor. This is our equation number 4 here. And now we want to write the equation of this mechanical rotational system. This mechanical rotational system, what we imagine here is that there must be a load, so we imagine that there will be a moment of inertia, and similarly this shaft will face a force of friction. So we model this system. The armature, the current in the armature produces the required torque. The required torque depends on the load connected to the motor shaft. If load consists only of moment of inertia and damper, as shown in the figure, the equation will become this developed torque will be equals to JD omega m. This is basically the moment of inertia at this point. Similarly, it will face a damping B omega m. So this is the developed torque. We can say that by using all the above equation, we can write in the term of motor velocity and displacement. What we can do, this is the torque developed, and this is also torque. I can use these two equations, equation number 2 and equation number 5, and if we substitute the values of this torque in the equation number 2 here, this torque developed due to the electric circuitry is basically this torque. So when we substitute these values, this will become KTIM JD omega m plus B omega m. I can evaluate the value of Im from this equation. What now I want to do? Basically, I want to write the system equation. System equation means here my input is basically the applied voltage, and I want to observe the behavior, which is basically the shaft rotation or the velocity of the shaft. Similarly, I can observe the displacement of the shaft. So I want to write this equation omega m over EA. Omega m is my output and EA is my input applied voltage. So I want to write this equation which is equals to in terms of omega m and EA. So what I did, I want to represent this Im in terms of omega m, similarly Em in terms of omega m. So for Em, we have this equation number 3 in which we said that back EMF depends on the angular velocity. So we can substitute this value here. I can evaluate the value of Im from this equation, and I can substitute this value in this equation number 4. So this is written here, using equation 2 and 5, I evaluated this Im and substituting values from 3 and 6. This is my equation number 6 into equation number 4, which is this equation. What we get this equation which tells that how this velocity, this whole equation is in terms of velocity, how this system velocity change with respect to the application of this voltage. This equation can be in terms of displacement as well. If omega m is my angular velocity, I can write d theta, means change in angular displacement is angular velocity. So this d will, the power of d will increase, and this will become d cube theta m. Similarly, d square theta m and d theta m. So we can evaluate the system equation of this DC servo motor. Similarly, we can use these equation to evaluate the state space representation, as we have two energy storing element here. One is basically this inductance of armature. Second is basically the moment of inertia at this shaft. We will model two-state variable here. X1 is omega m, which is basically the velocity of the shaft. By virtue of this, moment of inertia stores energy. Similarly, this is the armature current, armature inductance current. By virtue of that, inductor in that armature stores energy. So if you use the above equation, we can evaluate the value of x1 dash and x2 dash, which can be represented in terms of state space representation. Similarly, if we consider theta m as our output, another differential equation is required if the solution is theta m. If we want to know the displacement of the shaft, we didn't have any spring here, we will consider an augmented variable, state variable, and this will be theta m, and we can evaluate a third order equation. We will have three state equations here, and we can take third state variable x3 is equals to theta m if it is needed, if anyone is interested in the position of this system, so he may find the third state variable as well, x3, which is equals to theta m. So this is a basic DC motor model, which you can model it with the help of electrical and the mechanical rotational system. Okay, if you have any question, you can ask in the live session.